thank you for reminding me. Okay, so let's start our class. Today we are going to see some more details on the strain gauge rosette that we introduced last class. Just to remind you, the strain gauge rosette comes from this observation. If you have whatever strain gauge that is oriented in whatever direction with respect to a given reference frame, and the relation between the natural strain gauge measurement system and the reference frame is given you by the angle alpha, then we prove that the strain in the direction alpha is related to the strain in the xy direction as well as the shear strain from the equation that I've just wrote at the top of this page. That is perfect equivalent to the same equation in which I use the tensorial notation of the elasticity of the strain as well. Okay, so if I introduce d and n, being d and n the tensor, the strain tensor, and n is the unit vector, the cosine vector, then we can have the same information, that is the relation between the strain in the xy direction and the strain in the natural strain gauge direction, epsilon alpha. So what we got is that because we are using the strain gauge, we know epsilon alpha, and then we would like to have the information of the strain in these whatever directions. So in order to have that, because we have just one equation and three unknowns, we need to have three different measurements that refers to three different orientation angles. Okay, having said that, we now would like to have some more information concerning the strain in whatever orientation angle. Now let's assume to rewrite your epsilon alpha in a different way, but it doesn't matter. It is just a matter of fancy things. So we can rewrite that as epsilon x plus epsilon y half plus epsilon x negative epsilon y half cosine 2 alpha, and then plus the shear strain like that, sine 2 alpha. So this is a different but perfectly equivalent way of relating two different reference frame, alpha and xy, like this. Now, the question now that I would like to ask you, is there a specific direction in which the strain in the direction alpha is maximum? So I write the equation. Is there the problem? Is there a specific direction in which the strain in the direction alpha is maximum?
Is it 45 degree?
I can't hear you very well. Can you?
Pi over 4, I mean, 45 degree.
Oh, no, it's not say that. We can't say that, generally speaking. So the answer to this question is we don't know. I can anticipate you that is yes, there is, but we don't know in principle. In order to find out that, we can review the strain relation as a function on alpha, and then find alpha so that the strain is maximum or minimum and find out what happened. So we have to solve. The answer is found by solving this relation. That means if you make the calculations, that means that you have to find out the solution in terms of alpha p of this equation. Okay, so alpha p is by definition the principal angle for strain, and just by answering to your colleague, it is not said that is equal to pi4, of course. It could be whatever, depending on the value of the epsilon xy and epsilon x and epsilon y. Okay, so we found this alpha p, okay, that is the strain, the principal angle for the strain, and the corresponding value of the strain could be found both maximum and minimum just by introducing that in the previous relation. Okay, and the minimum value is epsilon evaluated when alpha is equal to the alpha p plus minus half pi. Okay, so this is the answer. But from the physical point of view, what does it mean? It means that when we are at that angle, that is, remember, the strain is a tensor, so depends not only on the position in which you are taking the measurement, in which you are evaluating the strain, but also in the direction in which you are looking at the strain in that point. Okay, so if you look from a specific direction, this alpha p, this principal angle, we found out that the strain is maximum, the normal strain is maximum, epsilon alpha, because it's the one that is measured by the strain gauge, and the corresponding shear strain is 0. So the alpha p is the principal angle for the strain, and the corresponding epsilon xy when alpha is equal to alpha p is 0, no strain at all. Okay. By the way, we can also prove that there is a specific angle, orientation angle, in which we maximize the shear strain, epsilon xy. Okay, we can prove that the epsilon xy maximum is equal to the difference in terms of amplitude between the maximum and the minimum strain. And this happens when alpha xy maximum is equal to the principal value, the principal angle, plus minus pi4. Okay, so the angle in which we are having the maximum shear strain is shifted by pi4 angle with respect to the principal angle for the strain. Okay, by the way, we can also have the same result as we got here in terms of maximum and minimum strain just by referring to the strain tensor. So what does it mean? Is there a direction? So I make the other question. Is there a specific direction for which there is no shear strain? The answer is yes, of course. And the solution is found by solving this problem. Let's take into account the strain tensor. Now we would like to have the cosine directions and that is specific for the maximum or minimum strain, that is not shear strain at all. And that should be equal just to the normal strain. We don't know that, so we can write it as, okay. Of course, the components of the cosine vector n are unknowns, and that is the solution. If you know these components, then you find out the specific direction for which there is no shear strain. As you can see, the strain given in whatever direction n is set equal to just normal strain because it's proportional to the cosine vector itself. That means you have to solve this, I hope, very well-known problem, that is the eigenvalue problem associated to your strain tensor. Okay, so the solution the solution is giving you from n the principal direction, and in a 2D way, that means alpha p, as we called that before. And here we are having the maximum or minimum just by shifting of half pi angle. Okay. So as we can see, once we have, going back here, the strain gauge rosette that is giving you the information of the strain in the natural strain gauge measuring direction. And we have this information corresponding to 3 different angles. Then we can solve this problem, okay? And therefore we can have epsilon x, epsilon y, and the shear strain epsilon xy, in which xy is whatever reference frame, okay? Of course, by changing the reference frame xy, we have different values of alpha, so those things are related to one another. Okay. Now, once we solve that system of equation with respect to epsilon x, y, and epsilon xy, we can use them to find out a specific direction, a specific reference frame in which there is a maximum value of the normal strain, maximum or minimum. We proved that this value is given you by this alpha p that could be obtained by that equation from the tangent of 2 alpha equal to that ratio, or just by solving the corresponding, here it is, eigenvalue problem associated to the corresponding strain tensor. Okay, I also introduce you the direction in which there is the maximum value of the shear strain. This direction is shifted by pi4 angle with respect to the principal one, to the principal direction, and the values is given, the value of the maximum shear strain is the difference between the maximum and minimum strain. Okay, just to give you an idea on how these orientation angles are located, let's have your reference frame, basic reference frame like this, X and Y. By solving this problem, once again, tangent of 2 alpha p and so on, we find out the angle alpha p. This alpha p, let's assume to have this value. Okay, so here we have the principal direction for the strain. Okay, then by shifting that by pi4, we have the principal direction like this, let me call that X shear, and X normal strain, okay, Y normal, and here Y shear. And of course, that orientation angle is pi4. Okay. So now let's see how we can use that. So let's image for a while that we are going down the laboratory and we are taking some measurements. Okay. So let's have an example that could be considered taken from the actual measurements. Okay, so let's have your strain gauge system that is intended to measure the strain in this point. Okay, these strain gauges are located such a way that they are like this, for example. 1, 2, and 3. So I have my strain gauges, 3 strain gauges. I am emphasizing that, so they are sort of magnify what you are seeing. Okay, this is, for example, strain gauge number 1, that is strain gauge number 2, and the last one, strain gauge number 3. Okay, now let me introduce, for example, additional given reference frame that is your X and your Y. Okay, so the question is, what are the strains in that point, the origin of the reference frame, in the XY direction? Let's assume that our measurements are giving me that the first strain is measuring, for example, 50 microstrain, 850 microstrain, epsilon 2 negative 100 microstrain, and the third microstrain is giving you 350 microstrain. That is from measurements. Let's assume to have them. Okay, so let's apply the previous equation. So we have 3 equations to apply. Okay, so what we got is, I'm just writing the first one, 850 is equal to epsilon x cosine square 0, because the first strain gauge is characterized by this one angle that is 0 plus epsilon y sine square 0 plus epsilon xy sine 0 cosine 0. Let me call this angle as alpha 2 because it's the angle of the second strain gauge with respect to the x-axis, and the other one is of course alpha 3. Let's assume that alpha 2 is equal to 85 degrees, alpha 3 is equal to 75 degrees, of course change of sign. What we find out that is that if now we apply the same equation as before, but now using the second and the third angle, what we found out is that first, from this trivial equation, we got that epsilon x is equal to just 850 microstrain. That is the case because the first strain gauge is located over the x-axis. Then, by applying the two angles alpha 2 and alpha 3 and solving the problem, what we got is epsilon y equal to negative 3.4 microstrain, and the shear strain epsilon xy is 1185 microstrain. Then, what is the direction of the principal reference frame for the strain? Let's solve tangent 2 alpha p equal to the ratio, as I told you before, so 1185 over 853.4. Okay, that is a summation of the first and the second gauge. That is, sorry, epsilon x negative epsilon y, and that is equal to 1.39, to which correspond a principal angle of about 27 degrees. Okay, so if you go back to your starting point, then you can say that 27-degree shift from the x-axis, you have your principal strain for the normal direction. YP, okay? This is alpha p equal to about 27 degrees, same as before. Okay, what's the value of the strain in that direction? What we can find out is the maximum strain is 1153.4 microstrain, just substitute the number, okay? And the value of the minimum strain, normal strain, just substitute the shift of 19 degrees plus minus 90 degrees is equal to negative 305.3 microstrain. And finally, the shear strain that we can have at maximum, that is orientated at 27 plus 45 degrees with respect to the x-axis. Okay. So it is something like that. So for the shear, just to be sure not to be misunderstood. Okay. Then it is equal to 1452.6 microstrain. Okay. That is your first interesting result that you got from that strain field. Okay, now let's assume, for example, to evaluate the strain, okay, we are in a 2D elastic domain. If aluminum alloy, for example, that is the Young modulus is 70 gigapar, and the Poisson ratio is about 0.32, then what we can say is that the maximum stress that the structure is subjected in the principal angle, of course, is given you by this very well-known formula. I hope so. And the minimum is in the orthogonal direction as well. Okay, just plug in the numbers. You got that is equal to 82.3 megapar, and the minimum value is 4.97 megapar. The shear stress, let me call it xy maximum, is E over 2 1 plus E epsilon xy maximum, that is G epsilon xy maximum, and that we have that the value is 38.55 yes, megapar. Okay, this is just an example. This is let's say just playing with numbers. But now, from the test point of view, I would like you to introduce a possible uncertainty of the orientation. For example, so positioning of your strain gauges, let me go here, is not that accurate. Just to have you a feeling of what's happening. Okay, let's assume that you are putting your strain gauges, and generally speaking, 1-2 degrees in uncertainty with placing that strain gauges by hand is something very, very accurate as well. Okay, but however, let's see what happens if there is, let's say, 3 degrees in uncertainty. So if a positioning uncertainty of, let's say, 3 degrees is affecting the bonding of the strain gauge rosette. Let's see what happens. Okay, so if we are having this positioning error, what we are having, for example, epsilon x still stay with the same number because it's the starting point, but let's assume increase with 3 degrees, then we have that epsilon y goes to 6.8 microstrain, and the shear strain is going to 893.6. I've just made the additional calculation, assuming that there is a change of the angle of 3 degrees, but the epsilon x. The resulting from the principal properties for the strain is that the principal angle moves to 23.32 degrees. The maximum strain, normal strain, goes to 1042.7 microstrain. The minimum value of the normal strain is negative 85.9 microstrain, and the shear strain maximum is going to 1028.6 microstrain. And the corresponding stresses are the maximum stress is 76.77 megapar. The minimum stress is equal to 11.51 megapar, and the shear stress maximum is equal to 32.58 megapar. Okay, now let's compare this result. These last three, for example, with these first three. So as you can see, we have the maximum stress in the ideal condition equal to 82 point something, and we move to 76. So we got a lot of effects on the estimate of the strain. There is a lot of effect on the estimate of the principal direction, principal value. That's the reason why we are not using self-made strain gauge rosettes, because the positioning error, the uncertainty in having the right angles, okay, the knowledge of the right angle, is telling you, is giving us, sorry, a lot of error, okay, when referring to the estimated quantities in terms of the principal angle, maximum, minimum normal strain, maximum shear strain, and so far and so on, okay? So that's the reason why, because of the relevant effects on the estimated quantities due to the position error. Strain gauges are not self-made, but we are using what we call photo engraved strain rosette. Okay, and that improves a lot the quality and therefore reduce a lot the errors in the estimates. Okay, so that's the reason why no self-made strain gauge rosette, although they could be used. But however, if you are doing self-made rosettes, then there will be the risk, and that is very probably that your measurement is plenty of error, uncertainty errors. Okay. Now, let's assume, for example, to find out graphically. I know it is a very old-fashioned thing to do using the strain gauge rosette, but it is better that you, as an engineer, had at least once touch with your hands the making of the more circle for the strain. Okay, so let's see together this more circle for the strain. And let's assume that the reference configuration is, once again, 3 strain gauges in this geometry. Let's say 1, 2, and 3, okay, that are with a given reference frame, for example, this one, let's say X, oops, and Y. Find out by the angle, let's say, this angle phi, then we are having alpha, and then we are having beta. Okay, and we call the strain measured by these strain gauges as epsilon 1, this epsilon 2, and this epsilon 3. Now, how can we find out the minimum and the maximum value of the strain and therefore the shear strain once we know that from graphical point of view without doing any calculation. This Mohr circle is helping us in doing that. How we can do that? Let's draw a reference frame, whatever, it doesn't matter, like this. This is just to say that this is not required to be just the one in the right scale. Okay, so epsilon, and therefore whatever value there, we place in this scale, in this axis, sorry, epsilon 2, for example, epsilon 1, and epsilon 3. Okay, then we draw 3 vertical lines like this. Okay, parallel to that dummy y-axis. Then what? Then we make a point here on the central vertical line, and by considering the orientation angle that the second strain gauge has with respect to epsilon, the first one, and the second strain gauge has with respect to the third one, we draw 2 straight lines that are taking these alpha and beta angles. So what we got is, for example, this line that is orientated with an angle alpha, and the other line, for example, like this, that is orientated with an angle beta. These lines intersect the vertical line passing through epsilon 1 and passing through epsilon 3 into 2 points. Let me call that this point A and B, sorry, A and C. This one is called D, sorry, I forgot to mention that. And then, considering these 2 different straight lines, that is the segment CD and the segment DA, we draw the median lines of the 2 straight lines like this. And this one. Okay, this line is the median line for segment CD, and this is the median line for segment AD. The intersecting point here that we call F, if a point that is having the same distance from CDA by definition. Now, if I'm drawing the circle that is passing through here, through this point D, A, and C, like that. Okay. Oh, sorry. I can do better, a little bit better. Okay, something like that. Sorry for that. You have a circle that is the Mohr circle that is telling you what is the minimum value for the normal strain, the maximum value for the normal strain, and of course, the maximum shear strain, just taking the difference between these 2 values. Okay, so it is the Mohr's circle. Okay, so that's it for today. It is important to me that we, let's say, we have some familiarity with numbers, strain gauge measurements, and we note that the uncertainty of the positioning of your strain gauge, or said that is the 3 strain gauges, could lead to very important, noticeable errors in the estimating quantity, such as the principal directions, normal strains, the maximum minimum normal strains, and so far, and so on. Okay, and then we had a tool for graphically obtaining this principal quantity for the strain that is called the Morse circle. Once again, how can we get that? It's very easy. Draw an horizontal axis that is the reference for your strain. Put on that horizontal axis these three strain measurements that you get, three vertical lines corresponding to these three measurements. Doesn't matter where you can locate the D point that is in between the 3 and 1. Then median lines, the center of the circle, and then the minimum value the minimum and the maximum values are giving you the principal value for normal strain. Okay, so that's it for today. Have a great weekend. Any questions?
Professore, mi scusi, non ho capito il raggio del cerchio, qual è?
Il raggio del cerchio, so the radius of the circle is by default whatever distance between the F and the A or D or C, because the F point is obtained by intersecting two median lines, okay? So the F point, this intersection is at the same distance between point A and D, but also C. So that's the reason why it is the center of that circle passing through C, D, and A.
Ok, grazie mille.
Prego. Other questions?
No, professor, thank you.
Okay. If there are no questions, have a great weekend. See you on Monday.
Arrivederci.
Arrivederci.